Hello, my name is Robert Borngle, and this is my presentation on the max-flow min-cut theorem and the Edmonds-Karp algorithm for CS5200 analysis of algorithms. So, a little bit of definitions. Some of this will be duplicate from the previous video, but notably, I have switched from using E as the ending node vertex to T as the terminal vertex. Doesn't matter. So, additionally, we have this concept of a cut. And a cut is basically two vertex sets, S and T, which together make up the entire vertex set, but are each individually proper subsets of the vertex set. There's no real restrictions other than the fact that the starting node has to be in capital S and the ending node has to be in capital T. I'm going to use vertex and node interchangeably a lot. So then we can have the capacity of this set be the sum of all the capacities of the edges that go from a vertex in S to a vertex in T. So this edge here, and this edge here, and this edge here, and this edge here. But notably, there's no other sort of restrictions, such as all the vertexes have to be, if they're in S, they have to be close to S, so they have to go from S to T, or anything like that. The only restriction is that S has to be in capital S and T has to be in capital T. We'll place more restrictions on them later when we actually use them, but for right now, that's that. And then, this is kind of minor, but the value of a flow is the total amount of flow out of the start vertex minus the flow into the start vertex. So basically it's the total amount of flow moving through the network. Well, the total amount of flow transported from S to T. This is notably the same amount as the inflow to T. So the outflow to S is the same as the inflow to T because of this preservation of material. Material cannot be created, destroyed, or stored except at S and T. So, here's the theorem. Basically, this is kind of a redefinition of a flow network, just for convenience. We have three equivalent statements. F is a maximum flow. The residual network contains no augmenting paths, and the value of the flow is equal to the capacity of some cut. We don't necessarily know which cut, but there exists a cut. So I'm going to show the proof for this in three parts. Prove that 1 implies 2, 2 implies 3, and 3 implies 1, and then from there you can transitively get all other implications that you need. So the first one is F is a maximum flow implies that the residual network contains no augmenting paths. This one's not too bad. Basically, the residual network contains only valid changes to the flow, and an augmenting path goes from S to T. So you see, this is the existing flow, where there's the existing flow over the capacity. So this edge is capacity of 2 and has a flow of 2, capacity of 3, flow of 1. So residual networks, which we talked about last time, as you can see, have been created here, right? So we can do a kind of proof by contradiction, where we say that there exists a path from S to T, and we can see that one exists here, right? We can go here, and then here, and then here. But because this path has to go from S to T across all non-zero edges, we know that we can simply augment the original flow with this new augmenting path and get a higher flow, right? So we know that F is it can't be a maximum flow if there is an augmenting path. So now we prove that 2 implies 3. So if there are no augmenting paths, then the flow value is equal to the capacity of some cut. So this one's a bit hairier, but we're going to use this concept that flow cannot be created, destroyed, or stored within a set of vertices, excepting S or T. So we construct our S from all the reachable vertices from S. So lowercase s can reach everything in capital S, but because there are no augmenting paths, we know that we can't get from S to T. So we know that T itself is not an S, and so T has to be in capital T. Right, so now we've constructed this cut where some things are in S and some things are in T, and we cannot get from S to T because no augmenting paths. So we know that because we can't get, well, in fact, we cannot get from any vertex in S to any vertex in T because of how we've constructed them, right? And so if we look at the flows and their capacities, right, in the case where flow is not at capacity, then we would be able to get from set S to set T. So we know that this case cannot exist. This case, on the other hand, can exist because the residual will not have any forward edges. We also know that no backwards flow can exist because then the residual would allow for going from S to T, and we've already established that can be. But we can have edges which go from T to S, but their flow has to be 0. So kind of to wrap up, all the flow from S to T is either at capacity, or if it's going backwards, then it's 0. And because as the stuff moves through the network, by the time it gets to S, it'll be the same, right? So all of the flow out of S minus the flow into S will be all the capacities minus all the zeros, because all the backwards flow has to be 0. So now we have to prove that 3 implies 1. So basically every flow, and for every cut, the net flow across the cut is equal to the flow value. We can use the same reasoning whereby no stuff is created, destroyed, or stored within this set. So we know that it has to make its way eventually out of S. So we can take any subset that contains S, and we know that because it cannot be created, destroyed, or stored, it has to make its way out into T and into lowercase t. So from this, we can establish that no flow value can be higher than the capacity of any cut. Right, so if we do have a flow value which is the capacity of a cut, it has to be the maximum one. So now we're going to talk about the Edmonds-Karp algorithm. So Ford-Fulkerson doesn't actually have a method for finding a path. It only says what to do after you've got the path. That is, the path through the residual network. But we are guaranteed to increment the flow value, that is, by at least 1 for each iteration. So if we take the time required to find a path, multiplied by the maximum flow, we can say that that's the number of iterations. That's the amount of time that Ford-Fulkerson will take. Now, if we take Ford-Fulkerson and we use a breadth-first search to find the paths, we call that Edmonds-Karp. So we want to show that the distance from the start vertex to any other vertex, except S and T, never decreases. This doesn't really, it'll come in handy in a minute when we want to prove something else. But basically, we let V be the vertex closest to S such that the distance to V decreases whenever we do one iteration, one augmenting path. And then we let U be the vertex that comes right before V in the shortest path to V in the updated residual network. We knew that UV can't have been in the original network because then we'll violated one of the previous principles. So we know that the flow from V to U must have been increased. But if V to U increased, then that means that the shortest path, because we know that Edmonds-Karp always finds the shortest path has to go from V to U. So V must have been closer, which is something that we assumed was false, so we have a contradiction. So now we want to, ultimately what we're after is putting a bound on the runtime of Edmonds-Karp. So previously we showed that the distance from S to any vertex never decreases, or monotonically increasing, and then we're going to use that here. So at every iteration, because of the way forward focusing works, we take the minimum of all the capacities of the residuals, which means that one edge has to reach capacity at every iteration. We call that the critical edge. And so then when we augment the flow, then the edge essentially disappears from the residual because it can no longer go forward anymore. But we can go backwards, right? And notably, when we go backwards, i.e., choose its inverse, when we go backwards, then that edge will kind of reappear in the residual. But because we know that whenever at every iteration of Edmonds-Karp, the distance from S to the vertex has to increase, and in fact we're going forwards and then backwards, which means that the relative distances have to have changed, and so the one which was further now has to be closer, and the one which is closer which now has to be further. But because they can't decrease, they can only increase, we know that the one which is closer has to have been incremented by 2. So now we've got this bound such that every vertex can only become critical, as it were, on the order of V, the number of vertices. So we know that for every edge, it can only become critical on the order of V times, which is V times E. So then we take the original time complexity of forward Fulkerson, and we say that the number of iterations multiplied by the time to take an iteration is the total runtime complexity. And in this case, that is E times VE, which is just VE squared. So, on to the assigned problems, I guess, homework problems maybe. We want to establish some sort of capacity not just on edges, but on vertexes in particular. We can do this by taking all the incoming vertices and then piping them into a single vertex, and then duplicating it as a kind of a quote outgoing vertex, and having all the edges, all the original outcoming edges now are outcoming from this new one. So basically all of these edges go to here, and all of these edges come from here, and then between them we have an additional edge with the original vertex capacity. So this is kind of like a one big pseudo vertex. So now comes to the grid problem. As a brief recap, the problem says that we have to find what was the wording? Essentially, paths from some set number of start nodes to the edges of a grid, such that no two paths can use the same vertex. So, in this original problem, we have a bunch of places we want to start from, a bunch of places we want to end from, and we also have bidirectional edges. So, as mentioned earlier, we can in the previous video, we can create kind of bidirectional edges by simply adding another vertex and then having one edge which goes one way and then a circuitous vertex path back the other way, right? which triples the number of vertices. Triples the number of edges, and then adds an additional vertex for every edge. So, if we take a snippet of this grid, this is just a small snippet, the first thing we want to do is we want to make the pseudo edges, pseudo start and pseudo end vertex, also described in the last video, right? Where these are our place we're trying to escape from, these are our edge vertexes, as in like the edge of the grid. And then we take some super starting vertex and add an edge to every of the escape points. And then from all of the places at the edge of the grid, we can add edges to some sort of, meta or super ending vertex. So the second problem is that these edges, in this case there's 4 of them, but on the grid there'll be much more. We have to do the bidirectional vertex trick, or bidirectional edge trick, sorry. And then, as one final step, we have to apply a vertex capacity to each of the original vertices. We don't have to apply it to these pseudo vertices, right? Because really all that we care about is in the original network, no two paths can take the same vertex. So this is essentially a vertex capacity. I've removed the dotted because it would be way too many edges, but these are just the on this snippet, the edges that we want. And so then what we do is we essentially take this graph and we run it through Edmonds-Karp. And we know that the runtime complexity of Edmonds-Karp is VE squared, but we've done a lot of updating. So our new V and our new E are, our new E is number of vertices plus 3 times the original number of edges, plus M, which is the number of starting points, and E, which is the number of exit points. And this is from the way that we've constructed all these modifications we've done. And the new number of vertices, this should be V prime, is 2 times the original number of vertices because of these, plus 2 for the meta vertices. Oh, I also forgot that there should be an additional vertex for every one of these edges, if that makes any sense. Because of the way that we've done our double edges, each double edge also has an additional vertex. Okay, I've tried to keep it short and concise, so there it is, 17 minutes.